afternoon. It was 15 according to my clock, and that my watch, and that.
Wait, there's still 1 minute. According to my clock, I still have 1 minute.
Okay, I have 1 minute to make an announcement. So, by popular demand, the second talks in the afternoons have been moved to 4 o'clock, so that we have all more time to drink tea. Okay, so Ivan's talk will be at 4 o'clock today, not at 3:45. Okay, and so you ready now? Okay, so the first talk in the afternoon will be by Nikita Nekrasov, and so according to the schedule, it's about BPS CFT correspondence, but you will know what it is by the end of the talk.
Thank you very much. It's I don't see Pasha here. Well, it's still a pleasure to give a talk, to give a talk on. So he will learn about my pleasure eventually. So I gave the rather general title because I didn't know what I was going to talk about, and I still don't. But anyway, at least I would like to promote the concept. So the BPS CFT correspondence it's sort of a principle which was proposed about 10 years ago, which states that the correlation functions of supersymmetry protected quantities in well, in gauge theories, but actually, well, maybe in more general context, in gauge string theories, are equal or are given by some other correlation functions in some CFT-like theories. So these are typically two-dimensional theories with infinite-dimensional symmetry algebras. They don't actually have to be conformal. So CFTs in quote marks. These could be massive deformations of conformal field theories, which have quantum deformed symmetries. So this could be theories which have Virasoro symmetry, Kac-Moody finely algebra symmetries, quantum deformations of those, and so on and so forth. So this could be, for example, lattice models as well.
So they're basically integrable theories, right?
Mostly integrable theories, yes. Again, this is a principle, so it means that it is ill-defined, and it will take. So it took already 10 years to come up with many examples, but maybe there will be more developments, and maybe during this conference as well. So some famous, well, the sort of outcomes of this correspondence. Well, one of these is the so-called Zyberg-Witten theory. Which relates the low energy effective actions of n equals 2, d equals 4 theories to some algebraic integrable systems. And so these algebraic integrable systems, you should think of those as of some sort of quasi-classical, heavy conformal dimension limit of some conformal field theory. And low energy effective actions of n equals 2, d equals 4 theories are actually supersymmetry protected. So the effective theory has supersymmetry, and the expansion and derivatives which we are able to compute actually can be cast as a correlation function of that sort. So that's one example. The correspondence between Gromov-Witten theory and, let's say, Donaldson on the one hand and Donaldson-Thomas on the other hand is also an example of such correspondence. So in Gromov-Witten theory, you study holomorphic curves in some manifold, some symplectic manifold. In Donaldson theory, you study invariance of the four-dimensional manifolds using gauge theory. And Donaldson-Thomas, you study also some kind of invariance of six-dimensional manifolds, three complex dimensional varieties. And it's not accidental that 6 plus 4 is equal to 10. So the correspondence actually uses one of the pictures which you have in mind, that critical string theory lives in 10 dimensions. So this 10-dimensional space-time of string theory is a kind of a correspondence in a mathematical sense between the 6-dimensional and the 4-dimensional physics. So this is the 10-dimensional world. Another aspect of this story, which I've been working with Samson Chatashvili in recent years, is the so-called beta gauge correspondence. Beta for Hans Bethe, not because it's a beta and gauge theory. And so this states that the supersymmetric vacua of theories with two-dimensional super-Poincare invariance they are beta states of some quantum integrable system, for example, lattice model. And so today I want to, perhaps I will, maybe the best outcome of today's lecture is to prepare ground for talks by Andrei Konkov tomorrow, and maybe it will also be useful for Sergei Lukyanov's talk, if time permits. So I want to focus on one aspect of this correspondence, just to give you one example, which is more or less concrete and which might be useful for understanding. And also for sentimental reasons, this is the example around which everything revolves all the time. So I want to discuss certain quantum integrable system, which many of us like very much, which is the elliptic Calogero-Moser system. Both for finite number of particles and also in the hydrodynamic limit. So n goes to infinity, and in the so-called chiral part, the so-called chiral part of the larger limit of this system. So I will try to convince you that knowing the supersymmetric gauge theory, whose vacua correspond to the stationary states of the system, is useful for understanding some of the properties of this model. So quantum integrable system, quantum.
What is hydrodynamic limit? What is this?
Hydrodynamic limit, yes, hydrodynamic limit.
I thought you were from a thermodynamic limit.
What Calogero?
And where's the size of the system so we understand?
The size of the system was finite. It's-
No, but are
I will introduce. I will.
particles in a finite volume or not?
This will be an infinite number of particles in a finite volume. Yeah. So these are kind of tiny particles. Okay. But before I go there, I probably want to make a sort of the. So all these correspondences are ill-defined mathematically. So these are some physical ideas which, even on physics, by physics standards, are not quite established. But the consequences of these ideas can be tested mathematically in conventional ways. And one can ask, what is the core? So the core duality, the core, the essential ingredient in which makes this whole machinery work. And I tried to come up with the simplest, with the essence of these dualities. And I guess the essential ingredient in what we are doing uses the following duality, which in string theory we're actually familiar with. It's the duality between the topological charges and, I guess, I don't know how you call them, dynamical charges. And well, actually, symmetry. So what I mean, so let me give you the simplest example of this duality, which everybody is familiar with. In T-duality of the fundamental strings, you have a duality between the winding modes and the momentum modes. So the momentum is a generator of rotations around some circle. So it's a symmetry generator which corresponds to the actual symmetry of the system. And winding modes, so they come from the fact that you study maps of a string, of a circle into some space with non-trivial topology. So this is a topological charge. And classically speaking, it does not correspond to any symmetry. It's just comes from the fact that your configuration space has components. Yet we know that there is some non-local transformation of variables on the string Lagrangian and the Walsh Lagrangian, which actually exchanges these two types of charges. Now, now, of course, everybody knows that thinking about this duality in a more general context leads to mirror symmetry and lots of interesting predictions. The kind of duality which I'm going to use in most of these constructions is the duality between the instanton charge so this is now, this duality comes from the sort of M theory, string theory duality. So instanton charge, so these are four-dimensional gauge instantons, which you could think of as, so these are like, you can think of them as of the winding modes in the space of gauge field configurations. So this comes from the fact that the space of gauge fields, let's say on S3 divided by the gauge group, has non-trivial fundamental group. So this is also some kind of a winding mode. And now you can ask whether there is some kind of a T-duality which will exchange this topological charge, which again does not correspond to any symmetry, with some momentum mode. And in string theory, we know that this is indeed the momentum in 11 dimensions. So this is the so-called number of D0 branes. And D0 branes are the Kaluza-Klein modes of the complexification of 11-dimensional M theory on the circle. So the instanton charge is the generator of rotations in some of some circle, which is somehow hidden in the gauge theory description.
Instanton charge is what? The last one.
Second,
Instanton charge is.
this is the instanton charge.
Current. You mean?
No, this is a charge. So this is a number. So if you think about, let's say, 4+1 dimensional theory, then this charge is a number of particles. So the instantons, you can think of instantons if we had 4+1 dimensions, if space is 4-dimensional, the instantons are sort of localized. They look like particles, solid tonic particles in 4 dimensions. And this charge just counts a number of such particles. And the claim is that these particles are actually Kaluza-Klein particles of reduction of some theory on the circle. So the fact that the instanton charge is the generator of rotations makes it, mathematicians sort of stumbled upon this fact before M theory was invented for example, in the work of Nakajima on representations of, let's say, Kazhmoudi algebras in the homology of the modular space of instantons. The instanton charge actually corresponds to the energy operator. So that's so energy is not exactly the same thing as a momentum, but it is for the chiral modes. So the chirality projection is somehow related to the supersymmetry, and so that's a physical explanation of relation between the instanton charge and the symmetry generator. And so this basic identification is actually the key to most of the constructions which I'm going to discuss. Of course, when you get down to the actual formulas, it's very hard to make explicit use of this relation. You can only observe that that's the way things work. OK. So now I want to be specific, to talk specifically about this model. And I'm going to talk about the elliptic Calogero model system of type A, n+1, and A-1. Because then I can take this limit. This is called Nikita. From Berlin. I don't know who it belongs to. Okay. So on one hand, this is just the system of particles. We have n particles on the circle, and I will assume the periodicity of the circle to be just 2π. These are non-relativistic particles. So it's interesting that I'm going to talk about the relativistic quantum field theories, but this auxiliary, this dual quantum integrable system is just of a type which you find in the textbooks on classical mechanics. So you have a kinetic energy, and then you have potential energy, and I may be off by a factor of 1/2 here. So there is a coupling constant which is conventionally written as nu times nu minus 1. P is, okay, I will put so I will keep h bar explicit, and if I keep h bar explicit, then actually there is h bar here. So this is the quantum correction. And now the pay function is the okay, my normalization. This is It's a doubly periodic meromorphic function. So it's a meromorphic function on elliptic curve with the second order pole at one point.
So this is equal to P of X. You're wrong.
Equals to P of X. Thank you. Thank you. OK, so P of X behaves as 1 over x squared when x goes to 0. OK, so if you want this Hamiltonian to be, if you want the classical Hamiltonian to be real, you would assume tau to be purely imaginary. But we will actually deal with more general systems when tau is allowed to be anywhere in the upper half plane. Yet you want to you want to find wave functions which are L2 normalizable and actually symmetric. So you impose the periodicity along one of the two cycles on the elliptic curve. And of course, in the general story, you may have different choices. So this is my choice. I want my particles to live on one of the two cycles on the elliptic curve. But of course, there is another obvious choice to make a dual cycle, to make a live on a dual cycle. It doesn't change much the problem. You just trade tau to minus 1 over tau. But you could also think of other choices. So OK, first, there is also the PQ choice when you make a so make particles live on a cycle which winds p times around a cycle and q times around the b cycle. That's also for p and q which are mutually prime. This is just a L2Z transform of the original problem. So this, if you know the spectrum of that problem, you know the spectrum of all these problems. But you could also make the irrational winding, and that also might be interesting. So then it means that your particles actually live on the line, and they interact with some kind of quasi-periodic potential, which has which has a peculiar property. I don't know what's the physical context where such a problem could arise, but I imagine. Why not? So there is a parameter here, the angle of the winding, which could be irrational. And so then,
in this case, the Hamiltonian is not real.
No, it's not real. In most cases, it's not real. So this could be of course. I mean, one context where this problem arises is the study of conformal blocks on a torus in theories with SLN Kac-Moody symmetry and the analytic continuations. So there, the reality is not an issue. But of course, the problem from which I derive this is gauge theory, and there, all parameters are actually complex. So let me now explain what is the gauge theory which is dual to this. So the gauge theory is a so-called n equals to 2 star UN supersymmetric Young-Mills theory. So it's a theory of the gauge field in 4 dimensions.
What does 2 star mean?
I will explain now. So 2 means that it has n equals 2 supersymmetry. It has 8 supercharges. Super young mules means that it contains gauge fields. And star means that in addition to the vector multiplet with UN gauge symmetry, it also contains the hypermultiplet in the adjoint representation. And star means that this hypermultiplet has a mass. So this is so the theory, as it said, the bosonic content of the theory is that of the gauge field and 6 scalars, all in the adjoint of UN.
So the Lorentz scalars.
They are Lorentz scalars. Lorentz scalars. Plus, you have, well, depending on how you count, 16 real, 16 Majorana fermions, which are also in the adjoint of UN. And out of these 6 scalars, 2 are massless and 4 have mass. So this mass now so this mass actually it's a complex number. Its its absolute value is the actual physical mass of particles, and its phase is only visible by fermions. So it's some fermionic phase. Now the gauge fields have the usual Young-Mills Lagrangian. With a theta angle, and so there's a coupling constant in the theta angle, and out of these 2 parameters you can form a complex combination, which is this combination tau. And the unitarity of the gauge theory, the fact that the coupling constant is positive, translates to the condition that the imaginary part of tau is positive.
Which is the hypermultiplet?
And so this hypermultiplet is formed by these 4 scalars and some fermions. So these belong to the hypermultiplet.
If it were not star, then?
And these belong to the vector multiplet.
And if it were not star, then those 4 would be missing.
So there are, okay, so n equals to 2 star is a particular n equals 2 gauge theory. In general n equals 2 theory, you have some number of vector multiplets in corresponding, so with some gauge symmetry. So the general n equals 2 is classified by, so in order to specify the theory, you need to specify the group, the Lie group, the gauge group, and its representation. It's a representation of G, which has to be real. And there are some bounds, so not all representations are good. And so this theory corresponds to the choice of G, which is UN, and the representation is adjoint, just one copy of adjoint representation. The peculiarity of that particular theory is that this coupling constant is actually well defined. It does not run with the energy scale. It's one of the asymptotically conformal theories. So if the mass were equal to 0, then this would be the theory with exactly vanishing beta function for the gauge coupling, and that it's also known as n equals 4 super-Young-Mills theory. We heard talks about that already, and Ivan will be talking about it afterwards. Of course, the theory has other operators which have very interesting anomalous dimensions, and that's the whole n equals 4 integrability story. But as far as the gauge coupling is concerned, this parameter is well defined in the ultraviolet, and so the theory depends on it. And so the identification is that the elliptic curve on which the Calogero particles live has the complex modulus, which is the gauge coupling of the gauge theory.
Because 4 has more fermions.
No, it's the same number of fermions.
What does
This is just a soft deformation of n=4 theory. Just give a mass term to the hypermodes.
what happens to the model in the n=4 limits?
Well, in the n=4 limit, this becomes just free particles. So you see the mass goes to 0, means that this coupling constant is 0, and then you just get non-interacting particles. And, everything is sort of trivial. Well, okay.
If it goes to H, we also have 0 coefficient.
Yes. So, but I'm yet to explain what is H, because I didn't identify that. So, okay, in order to map this theory to that model, I need to perform one more deformation, which will actually, among other things, make it less supersymmetric, and it will make it sort of more natural effect that the vacua would form in the isolated set of a discrete set. Because before we deform the theory as it is actually has a continuous set of vacua, the states of zero energy, which are parameterized by the expectation values of these two massless scalars, which are usually combined into one complex scalar. And so you have the modular space of vacua, which is C to the n for the UN gauge theory, with some interesting metric. So this so it's a modular space. And this modular space of vacua is actually it's the base of the classical algebraic integrable system, which is the system where you just view now P as the canonically conjugate variable to X. And a point on this modular space corresponds to fixing the values of all commuting Hamiltonians. So I wrote the formula for the one. There is another, which is just the overall momentum. And there are others which you can compute by using the Lux representation, which was found by Krichever in 1980. So out of by studying the invariance of this matrix, which depend on auxiliary, well, which in itself lives on an elliptic curve, the same elliptic curve, and it has a pole at one point. So by studying the invariance of this function, of this matrix, if you like, you can expand in your favorite basis of functions which have a pole at z equals to 0. You will get some set of is a bad letter. Sorry. You'll get a set of Poisson commuting functions, which in fact there is exactly n independent ones. And so fixing the value of these Hamiltonians actually is equivalent to fixing a point in the modular space of vacua. And in fact, the correspondence is that, roughly speaking, the value of these Hamiltonians is equal to the expectation value in the gauge theory of the operator trace phi to the k, where phi is the scalar in the adjoint representation. It's actually a bit trickier than that, and I gave infinite number of lectures here last year.
Is a matrix of what size?
Phi is the adjoint of UN. It's n by n matrix.
The same number as
It's the same number as here. It's the same number as here, but it is not correct to just identify them literally because, well, this is a field in the four-dimensional gauge theory, so it a priori depends on 4 coordinates. Just in the vacuum, it doesn't. And this guy lives on an elliptic curve, and this elliptic curve has nothing to do with the 4-dimensional space-time where the gauge theory lives. They live in orthogonal worlds, but they know about each other. So this is one of the correspondences which I started to talk about. And then the A's, the eigenvalues, the closest to the eigenvalues of this field phi in the vacuum are the action variables. For this model. Now, so as I said, so you have this is the continuous modular space of vacua, and in quantum theory, in the quantum integrable system, where we impose the condition that so we will look for the L2 normalizable periodic eigenfunctions, the spectrum of these Hamiltonians will be discrete. At least that's the expectation, because this is a repulsive potential. So every 2 particles, the relative motion of 2 particles, of every 2 particles is finite. So you expect a set of discrete levels.
In the real case, right?
Second?
In the real case, when tau is imaginary.
Well, okay, so if for tau is imaginary, you can draw it like that, and so you expect that. But then if you give tau some real part, the picture shouldn't change drastically. So the energy levels will become complex, but they will still be discrete. So what we expect is that we will get some discrete set of points which would correspond to the spectrum or the continued spectrum of that problem. Indeed, we can start with a gauge theory which has vanishing theta angle, and that would correspond to tau, which is purely imaginary, and then we would expect these eigenstates, the surviving vacua, surviving the deformation, which I'm yet to explain, which would makes this a quantum theory, quantum model, not classical, to align along some real submanifold. So they would sit inside R to the n. But then, once I turn on the theta angle, they will start wandering in the complex domain. And then there is some interesting monodromy, and then there is a whole story about the level crossings and all kinds of interesting phenomena. So, okay, so on the gauge theory grounds, we actually expect it's actually very rare that the theory has a modular space of vacua. It's only when you have an extended supersymmetry which such a behavior is natural.
Nikita,
yes.
Quantization condition that single out this discrete.
I will write them down. Yes, I will write them down. So there is some. So there is some function of this eigenvalues A, which has a meaning of the twisted superpotential of the effective theory, And the condition that the derivatives of this function are integral singles out these discrete points. And this function in itself is some kind of deformation, quantum deformation of the prepotential of the classical model. OK, so there is a deformation which breaks four-dimensional Poincare invariance, super Poincare, down to two-dimensional super Poincare invariance, which which utilizes the rotational symmetry of the original theory. And mathematically speaking, you pass to the sort of equivariant homology with respect to the rotations. Use rotations in two dimensions. And physically, what you do, you do the following trick. Which you actually can do in many instances. So the general trick is the following. Suppose your quantum field theory in d dimensions is obtained by dimensional reduction of some other quantum field theory which lives in d+1 dimension. So then what you can do, you can take this QFT prime, treat this +1 dimension as time, and then spin your theory. So you introduce angular velocity. So I'm assuming that the theory has Lorentz invariance. So once you have a theory with Lorentz invariance, you can put it in the background, in a rotating background. Of course, if everything is non-compact and time is non-compact, this is just passing to another coordinate system. It doesn't do anything. But if you fix asymptotic conditions, then actually you do change the physics of the model. It's like taking black hole and replacing it by a rotating black hole. Rotating black hole is different from the static black hole. And now, but now the trick is not over yet. You now forget about time. So you go back to d dimensions. But now you have deformed your theory. This is like the story about the old man who was trying to divide his property between his sons, and then it wouldn't divide, and then he invited a passerby, and so then they managed to divide, and then we had one left. And so this is something like that. So in the end, you get a theory which no longer has translational invariance, because you used rotation about some axis, and it is some sort of deformation of the original theory. And so for this particular problem, I'm using rotations in 2 out of 4 dimensions, and so I'm adding to my original Lagrangian some terms which couple the angular momentum of various modes. And there is a parameter which I call epsilon, which has the meaning of this angular velocity, and the angular velocity has dimension of mass. Yes.
You talked about angular velocity, you'll be breaking Poincare invariance.
Yes, that's what I said. I'm breaking the Poincare invariance in this two-dimensional plane. So I had 4-dimensional Poincare invariance, and now I have only 2-dimensional Poincare invariance. And there is a preferred, so there is a preferred, in the region of four-dimensional space-time, there is a preferred two-dimensional plane about which I'm rotating. And now I'm doing this in a way which is consistent with some supersymmetry. So in fact, there is some sort of localization of degrees of freedom onto this fixed plane. And so the final claim is that the identification of the quantum integrable system with the vacua, with the space of vacua of the gauge theory involves the identification of the Planck constant of the many-body system with the rotation parameter on the gauge theory side. And so that's sort of the coolest part of it all, that the Planck constant, which is sort of the coupling constant, which is a mysterious parameter, here becomes a geometric parameter. It's just it's the covariant. Well, for mathematicians, this is just the covariant parameter corresponding to the rotational symmetry, and for physicists, this is the angular velocity. And so this is it's a baby version of the grander picture which we try to understand with M theory, where the M theory does not have any parameters, any coupling constants, and once you compactify it on a circle, you get a theory in lower dimensions which has a coupling constant, and the coupling constant is related to the size of the circle. So it's again the geometric parameter becomes the Planck constant of the system. And this is a baby version because here the role of the mysterious M theory is played by the gauge theory, which is more or less understood, and the role of the type 2A string theory, which is also complicated, is now played by this innocent many-body system. All right. Now, what do we know about the theories which have two-dimensional superpointary invariance? So you see, the point is that even though this is the theory in an infinite volume, the presence of this angular velocity creates a potential well for most modes, and so effectively they actually sit in the potential in this direction. They sit in the finite volume effectively, and this volume is of the order of 1/epsilon. And so if you look at the system from far away, you see two-dimensional supersymmetric gauge theory, and in 2 dimensions, so it turns out to be a 2,2 supersymmetry in 2 dimensions, and there are basically 2 famous types of multiplets in 2-dimensional n equals 2 theories. The chiral multiplets, whose dynamics is typically governed by a superpotential, and these become the famous Landau-Ginzburg models, which people study a lot. And then twisted chiral multiplets, whose origin typically is the gauge multiplets. And so instead of the Landau-Ginzburg theory, here we actually get the twisted Landau-Ginzburg theory. So there is a twisted superpotential. Main character is a twisted superpotential, which is a function of, again, which is a function of scalars in the twisted chiral multiplets, which are the same as scalars which we got in 4 dimensions. To gauge supermultiplet. And now for the superpotentials, the ground states of the model correspond to the critical points. So usually, if for superpotential, if you have a superpotential which depends on some chiral fields, there is a potential term in action which is the norm squared of the gradient of the superpotential. And so for the vacua, you look for the critical points. Now the twistor superpotential interacts with gauge curvature. And so the effective action actually is a bit trickier. There is a real part of the gradient of this twistor superpotential. And then there is an imaginary part which interacts with the gauge field curvature. So this is a gauge curvature. This is in 2 dimensions, so you can so you have an integral of a single curvature times this imaginary part. So if the curvature, if it were an independent field, which is the case for the auxiliary fields in the chiral multiplets, you would have integrated it out, and you would have gotten just the square of the imaginary part of the dw tilde over dA, and that would combine into the total gradient square. But in 2 dimensions, but this is a curvature of the gauge field, and so it is it has a constraint that its total integral is quantized. So it's not quite an independent field. And so it turns out that the equations which describe the vacua of the system, which is governed by the twistor superpotential, are described by this equation. So this space of solutions to these equations is still isolated, but you have a priori you have an infinite set of equations, infinite set of solutions, because you have an infinite choice of these integers. It is actually not that bad, because it turns out that this function w tilde, unlike the superpotential, which actually has to be single valued, or its derivative has to be single valued, for this twistor superpotential, even the derivative doesn't have to be single valued. It has to be well defined up to the shifts by imaginary integer. And so there is a compensation between the number of choices for this flux, now variable n, and the branches of this twistor superpotential. So anyway, to make a long story short, and I have 7 minutes to go, this function w tilde can actually be computed from the gauge theory, because all these manipulations which we used are compatible with supersymmetry, and so you can do the exact computations. And so w tilde of A is actually given by, well, can be computed in some sense. So it depends on the data of gauge theory, which I sketched already. So it depends on the mass of the adjoint hypermultiplet, and it depends on the gauge coupling constant. And so there is a tree-level term, which is tau over epsilon times sum over a squared. This is the term which actually gives rise to the standard kinetic term of the gauge theory localized on 2 dimensions. And then there is an interesting one-loop term, which has contributions from the vector multiplet of the original theory, the W bosons, and from the matter fields. So the matter fields have mass m. And so W1 loop is an interesting function. It's a which I will sketch later. And then there is an infinite series of instanton corrections. Q is e to the 2 pi I tau. So W1 loop can be computed using zeta regularization. And it is an analytic continuation of the following integral. It's a limit of the it's an asymptotic of the double gamma function of Barnes. And so its derivative is actually the logarithm of the gamma function. So if you neglect the instantons and you just use the tree-level part of W tilde and its one loop part and substitute into the equation for vacua, you will get an interesting equation describing the asymptotic spectrum of the elliptic Calogero system. So this is e to the up to some factors, 2 pi I tau ai times the product j not equal to I. Then there is a ratio of gamma functions. Which actually corresponds to the following problem. So actually, I lied. So when I said that I'm interested in the wave functions which are periodic with the period 1, I lied. So I'm interested in wave functions which are periodic with the period tau. So what these equations mean is the following: you take a limit when tau is very large in this P function. You take such a limit where it actually becomes 1 over hyperbolic sine squared plus e to the 2 pi I tau corrections. So this hyperbolic sine, inverse hyperbolic sine squared, is a potential which decays very fast at infinity, exponentially fast at infinity, and allows you can define asymptotic states. And so these equations describe the condition for a system of plane waves with momenta a1, an, of particles which have the two-body scattering matrix, which is given by the ratio of these gamma functions. So this is a two-body S matrix for the 1 over sinh squared potential with this coefficient. And then you try to impose periodic boundary conditions. So of course, this is not consistent because the potential is actually not periodic, but it fails to be periodic by exponentially small terms. And so up to these exponentially small terms, which are actually exactly taken into account by the further corrections, instant corrections, this is the asymptotic beta-ansatz equation for the system. And this is what Pasha suggested a long time ago, that this should be the approach to the elliptic Calogero system. And that's the way gauge theory gives this. And then there is a systematic expansion where with terms which come from the instanton effects in this gauge theory, which actually make the whole thing consistent. So now if you correct by at the first order in Q, then there is a correction here, and so on and so on and so forth. Times this, yes, times this. And unfortunately or fortunately, this two-body factorized structure fails. So once you add further instanton corrections, this is no longer a no longer two-body factorizable problem.
So you say that these are the wrapping corrections that I would have.
Exactly. Sorry. Okay, so I'm probably behind the schedule, so I don't have time to continue. But let me just tell you that the gauge theory analogy, or gauge theory intuition, allows the n goes to infinity limit, in which case so it's actually not only gauge, it's also there is a string theory, string intuition there. So you think of this gauge theory as living on a stack of large number of D3 branes, and when n becomes very infinitely large, well, there are different notions of large n limit, and here you take a limit when the space C to the n becomes actually the Hilbert space. So you replace the un by the group of unitary operators in the Hilbert space. And that actually corresponds to lifting this to a six-dimensional theory. So this actually becomes, so this n becomes fuzzy, and then you get a single D5 brane. So it's now a six-dimensional theory. And as it is, it's a very complicated theory, but you can actually focus on a subsector where you fix now not number of particles, but you fix the momentum. Yeah. So you fix now fix. Let me call it M, and that corresponds to considering a stack of M D1 strings which sit inside this single D5 brane. But now on the D1 strings, they correspond to 1 + 1 gauge theory. And it's a theory which actually is very well understood. It's a gauge theory whose metric content is that of the ADHM matrix model describing the modular space of M instantons on R4. And therefore, there is a corresponding twisted superpotential function, which is actually now will be a function of M variables. And so even though the infinite n theory, infinite n limit of this model is a system of infinite number of degrees of freedom, once you focus on the sector with precisely M excitations, you get a well-defined quantum integrable system with finite number of degrees of freedom, and its spectrum is described by Bethe equations, which are actually much even simpler than these ones. Oh, sorry. Yes, I should have said. So the eigenvalue of H2 is just the derivative with respect to tau of this function WA tilde of A. So W tilde is given by this formula. I didn't write the expression for the instanton corrections. That's a separate topic of a separate talk. Then you solve these Bethe equations. These are Bethe equations. And then you substitute it here. And that gives you the value of a spectrum. So asymptotically, you can actually solve this system, if you like, starting with just a simple solution that A is an integer over tau, and then corrected by gamma functions, and then by further corrections.
How do you take this derivative? Is it full derivative or partial derivative with respect to tau? Because
This is a derivative on the solution. It doesn't matter. On the solution, you choose the you compute the derivative on the solution of these equations. So all other derivatives are already fixed to be an integer. This is like the derivative of free energy or with respect to some parameter.
All other costs depend on tau.
Okay, this is.
Are you done?
I'm done. Okay, thank you. I'm done for now. If somebody asks, I can write this formula. Right? The formula for this potential is.
What are wave functions?
Okay. So gauge theory actually has potential for describing the wave function as well. Right now I cannot write the formula for you, but I believe it will be done in the near future. Yeah.
Okay.
No, it's. I mean, it's sort of remarkable that we get the equations for the spectrum without describing the wave function, but as with the other beta and Zatz problems, sometimes you can be quick and come up with the formula for the spectrum, but eventually you can also write the formula for the wave function as well. I didn't describe. So there are the additional ingredients which you need to describe the wave function. I didn't describe it in this stuff. I didn't describe it in this stuff.
So these equations for W tilde, they're exact, right? So
They're exact. Yes.
can you write them?
Yes. Yes. Okay. Thank you. Thank you. So these equations have the following structure. Times Q. So this is equal to 1. And now where S of x is just x plus. So you see, this is the S matrix of the up to some factors of I. This is just the two Magnon wave function for the usual XXX spin chain. And here you see that these magnons of this Calogero liquid behave as sort of as bound states of, I don't know how many particles. Actually, I would say an infinite number of particles, where if you view epsilon as the reference, so usually you can scale epsilon to be I. Then you have a complex spin. Then you have a spin nu, which is m over epsilon, and then you have the dual spin, which is minus. Well, maybe my normalization is not correct. I think it's 1 minus nu. So you have spins nu and 1 minus nu bound, and the spin 1/2. And here you have, you see, one factor like that. So you can think of this as a sort of a spin chain with one spin side. And when you think about this, actually, this is the spin chain with the symmetry, which is Yangian of U1 Kac-Moody. So the Hamiltonian of this Calogero becomes the well.
I have a quick question.
Yes.
So what are the BPS protected things that were
So this was
on the gauge side?
on the gauge side. So this was a superpotential, twisted superpotential. It's one of these F terms.
Computed, right?
Yeah, yeah. And the way we computed it by actually computing the partition function of the theory in this background and then taking some limits. And the eigenvalues of the commuting Hamiltonians, they correspond to the vacuum expectation values of the BPS operators like trace. So H2 corresponds to trace phi squared, H1 corresponds to trace of phi, and so on. Yes.
So if nu is an integer multiple of h bar, there exists a bit, and that's what
Yes,
Calogero
which is different. Which is different because in your beta ansatz with Varchenko, you had so your beta ansatz was a kind of a nested beta ansatz for the Godin limit of the XYZ spin chain actually. So it had if I remember correctly, it has something like n times n minus 1 times nu over 2 beta roots. And so Samson and I, we had a conjecture that there is a sort of a partial Legendre transform of your master function. So when you eliminate all the beta roots except for the last n, which would be related to our which will give our Young function.
Your beta ansatz is not nested.
No, it's not. No. It's a well, if you think about it, you see, even the finite n Calogero modular system here, it sort of corresponds to the GL infinity algebra. So it's not SLN. So it's a deformation of U1 Cosmodi inside GL infinity, and n enters as some kind of a choice or representation. And for integer nu, you can make a duality, which will anyway. So it's too technical.
It sounds like a broken record, but I would like to
Broken what?
record.
Yeah.
Repeat my confusion about this.
Yes.
Elliptical Calogero is elliptical. Right?
It's elliptic, yes.
So there is a certain democracy between tau and.
Well, it's the democracy which is broken by the choice of boundary conditions. So you have, so this is what I started with actually. So I said that there is an SL to Z, which acts, of course, but it does not. It maps one eigenvalue problem into another eigenvalue problem.
This which is in here.
It corresponds to a particular eigenvalue problem, which
Condition does
which is this problem.
So here's the confusion which I would have with this. It's elliptical problem, right? So naturally, one would expect elliptical objects in elliptic matrix, and therefore in the beta ansatz.
Yes, but of course, but
function.
no, but it's because here this is written in expansion. This is the expansion when around q goes to 0. So this is the expansion about the trigonometry, about the hyperbolic limit. So this is why it's broken.
Beta ansatz or expansion. Can you lift it up?
Well, okay. In my approach, my approach is all formulas are given as an instant-on expansion. Sometimes you can resum, but I don't know how to resum any series which I encounter into something which will be elliptic. But of course, I mean, if you don't ask for much, you can actually get more mileage. So you see this. So this W tilde function is actually it's a limit of a more general function which has more parameters. And you can see the elliptic structure actually in this function probably better. Let me just give you an example. So I don't have a closed form expression for this W tilde, which will make it obviously it's elliptic. It's here it's sort of a miracle that in the end everything is expressed in terms of theta functions and the derivatives. unlike Felder-Varshenko beta ansatz, where the ingredients are elliptic, but then you pay for that but then you need the nu to be integer. Here it's a different story. But anyway, so if n equals to 1, which is kind of a trivial case, of course, for this problem, but for the partition function, it's already non-trivial. This partition function, out of which the W tilde is one particular asymptotics. This is given by the it's essentially the Dedekind eta function. Sorry, it's the it's Dedekind eta function. So you see that the elliptic functions show up, but this is written as a sum over partitions, and then for each partition you have a complicated ratio of the hook length, hook arm products. So each term is some rational function of all parameters but q, and then when you resum, so you get something elliptic. The fact that you should get something elliptic is somehow already clear in the fact that all these partition functions are sums over the partitions. So n-tuple for the UN theory, it's sum of n-tuples of partitions, and so you can write this as a matrix element of some chiral algebra generator, some representation, and so then, in fact, for this n equals 2 star theory, this is typically the trace, q to the L naught, and then some vertex operator.
Okay, so I don't know. Let's. So, do you mind? So, I remind you that we will reconvene at 4 o'clock, and so the second talks starting from today will be at 4 o'clock. So